This is part 2 of the video series about pointers. Today we'll dive a little deeper and take a look at more advanced examples, but they won't be too hard, so no pressure. First, I'll explain why sometimes we use two different notations, i.e. char square brackets and char asterisk for strings. Next, I'll talk about how to modify struct from inside other functions, and finally, we'll look into linked lists so that you get to see pointers in action. Let's begin. Okay, so first off, what is the difference between char square brackets and char asterisk? While they're not the same, they actually capture a very important feature of the C language. It might sound complicated, but actually, when you declare an array and assign it to a variable, all this variable stores is a pointer to the first element of the array. Please take a look at this example. Let's declare a simple array of 5 integers and assign it to a variable r. Now let's see what happens when we dereference r and print it as an integer. See, it's the first element of the array, i.e. 1. Essentially, asterisk r equals r0 because r is a pointer, and asterisk r is the value of the cell to which this pointer points. What this means is that you can access elements in the array through pointers as well. Please take a look at this loop. Here, what I do is I simply increment r and dereference it to get the values in the array. This works because in arrays, data is stored consecutively, so you can calculate the address of any data in your array very quickly, which is why arrays are so fast. If you want to get the third element, for example, you'll need to go to the second address, i.e. r plus 2, and then use the dereferencing operator to get the value, i.e. asterisk r plus 2. This means that r0 equals asterisk r plus 0, r1 equals asterisk r plus 1, etc. What is neat about this is that you can add or subtract numbers to or from addresses of any type, even though they have a different size. You don't have to care about how many bytes you need to skip to get to the next value in the array, because the compiler does that for you. For example, a character takes up 1 byte of memory, and if you increment a pointer to a character, it will be incremented by 1 byte. However, if you do the same operation with an integer, then the compiler will automatically skip 4 bytes to get to the next integer in the array, even though you set pointer plus 1. This is a nice hidden feature that you don't have to care about. Here's the output of our code. As you can see, it works as expected. Now let's come back to why char square brackets and char asterisk can both be used to represent a string. Like I said, an array is a pointer to the first element in a series of elements that are stored consecutively in memory, and we know that a pointer is represented with an asterisk, right? Don't get confused though. This asterisk is completely different from dereferencing. When we declare a pointer, we denote it with an asterisk. So since an array is a pointer, we can denote it as a pointer, as in char asterisk. However, char square brackets is still different from char asterisk, so they cannot be used interchangeably. Char square brackets is a native C data structure, and the compiler won't allow you to change its value or do any mathematical operations on it. A char asterisk, however, is just a pointer, so you can change it however you want. Basically, it gives you more flexibility, but it doesn't mean that you shouldn't be careful with it. With this kind of freedom, you need to exercise extra caution to make sure you don't access invalid memory cells. If that is so, then why would I want to use a pointer, you might ask? Well, the thing with arrays is that they're not very flexible. Let's say you don't know how many characters there are going to be in a string, but you need to declare one, right? The compiler won't allow you to just say char x square brackets. It will complain and say that you need to specify a length. Let's say you set the length to a very large number, like 100,000. Then it turns out that your string only takes up 3 characters. What a waste of memory, right? In these cases, what you can do is you can dynamically allocate space for your strings, i.e. after your program is compiled. This is done with the malloc operation. What malloc does is it finds free memory cells of the size that you specify. For example, let's say we have a program that asks the user's name and stores it in a string. We find out that the user's name is Christopher, which is 11 characters long. What we need to do is declare a pointer to a character, let's call it name, and then say malloc size of char multiplied by 11. Why size of char, you might ask? Well, malloc needs to know how many bytes exactly you're going to need, and even if you know the size of a character, it's always a good practice to use the size of operation instead, because an integer might be 4 or 8 bytes long depending on your operating system. If there's not enough memory, then malloc will return null, so it's always a good practice to check if memory was allocated successfully. Otherwise, there might be a fatal error. Alright, so now we have enough memory for our name. How do we access it? Printing is done in the exact same way as with arrays of characters. Other operations like string copy and string length work on these kinds of strings too. What you need to be very careful about though is that you shouldn't assume that the compiler allocates enough memory for you when you just declare a pointer. Let's say you just copy Christopher into name without initializing it. This will throw a segmentation fault, so don't ever do this. The reason this doesn't work is that you haven't told the compiler where exactly to store your data and how much. All you did is just declare a single pointer. The reason I'm explaining all of this is because I want you to understand the second part of this video, which is about initializing structs from inside other functions. This can be handy when you want to keep your code in the main functions as clean and readable as possible. Besides, if you have a granular source code, it will be easier for you to recycle it instead of having to extract bits and pieces from a large chunk. Alright, let's go back to the person struct created in the previous video. Let's say we want to initialize a person from inside a function, and you would want to assign a name and an age to a person. I've created two versions of this function for you to have a better understanding of how pointers work. Let's take a look at the first function. It accepts three arguments: a person struct, a name as a pointer to a character, as was explained previously, and an age as an integer. All it does is it copies the values of the arguments into the corresponding attributes of the person struct. So far, so good. Now let's create a function that prints out information about our person. Again, nothing difficult here either. So far, we have granular, understandable code. Now let's jump into the main function and test the initialization function. See, the output is just gibberish. And do you still remember the last time we talked about gibberish? Yup, it's when a variable is not initialized to anything, not even null. And this is dangerous, remember? Well, we initialized everything inside our person struct in the function, so why is it not working? Well, the reason for this lies in the way parameters are passed to functions in C. What the compiler does is it creates a copy of each parameter instead of passing the actual parameters. What this means is that when you pass parameters like this, your function modifies copies of their values rather than their actual values, and whatever changes you made inside the function are only temporary. To fix this, what we need to do is tell the function where the values of our parameters are so that it knows where in memory to make changes. This is called passing arguments by reference, i.e. with an address. How do we find the address of a variable? Well, all we need to do is put an ampersand in front of the variable we want. In this case, we want the address of our person struct. Now let's try the second version of our initialization function, but this time we'll pass an address to our struct instead of its value. In this function, the compiler will pass a copy of the address of our struct, so we won't be able to modify it permanently, which is a good thing as it's not something we're looking for. Now that we have the address, we can easily go to the memory cell that has our person struct and modify its contents permanently. Let's test it in our main function. Yep, as you can see, it works correctly. If you understood everything we went through so far, then this part of the video will be a piece of cake for you. In this part, we're going to talk about linked lists. In case you don't know, a linked list is a sequence of structs pointing to each other. Here's a diagram that illustrates this. There's a bunch of structs, each of which has a pointer to the next struct. Technically, linked lists are like arrays because arrays are also lists of some elements, but linked lists are different. Unlike in arrays, elements in linked lists are not stored sequentially. Instead, they're scattered across memory, so you don't need to keep track of every node's address. You need to keep track of every node's address. That's why we need to have a pointer to another struct in each struct. This means that accessing elements in linked lists takes much longer than in arrays. This is not to say that linked lists don't have any advantages. It's just that they are suited for some cases better than others. We'll talk about the pros and cons of arrays and linked lists at the end of this video. But now let's take a look at how to create a linked list in code. Let's go back to the person struct. We'll need to make adjustments to our code. First, we'll need to modify our person struct. We need to add a pointer to the next person struct like this. We'll also need to modify our initialization function and set each person's next attribute to null. Again, it's always a good practice to initialize your variables. Now let's declare a bunch of people in a loop to avoid hard-coding stuff. Hard-coding absolute values in code is not a very good practice because it takes a long time to modify and is prone to bugs. The first thing that we need to do is declare a pointer to the first node and store it in a variable called head. This will be the head of our linked list. You absolutely have to make sure you keep track of the head because it's the only thing that can get you access to your linked list. Without it, you'll have no idea where your linked list is. The one thing that you have to remember about linked lists is that it's very easy to lose track of the head. So the best practice in this case is to never change the value of the head and instead just create copies of it. When you create copies of plain data types like integers, characters, and pointers, the original value is not modified. For example, if you say int a equals 5 and b equals a, b equals 10, then a won't become 10. That's also the reason why the head is a pointer and not a struct, as I'll explain later. Alright, we have to allocate memory for the head. We do this with the allocate memory function. Here's the function itself. Again, we're using malloc, so nothing out of the ordinary. Next, we'll need to initialize the head with meaningful data. Now let's create a copy of the head and store it in a variable called prev. If both head and prev were structs, then prev would have been just a copy of the head and wouldn't point to a completely different memory cell. It would point to a completely different memory cell. Basically, the head won't be updated if we do this. However, now both prev and head are pointing to the same space in memory, so we're all good. Now let's get to the main loop. Let's create 10 more people. First, we create a pointer to a temporary node. Next, we'll allocate memory for it. Then we initialize it. The sequence of these steps is very important. If you initialize before allocating memory, there will be an error. The next step is to attach this node to our linked list, and we use the next attribute to do this. We set prevs next to the new node, so now the new node is prevs neighbor. Finally, we set prev to temp in order to continue the sequence. We don't want to get stuck at the same two nodes, right? Basically, in this loop, we have two pointers, prev that points to a previous node and temp that points to the node we're currently dealing with. Maintaining both is very important to make sure the sequence is complete. Please take a look at this diagram for illustration. All of this might be messing with your head at this point, and I totally get it, so don't stress. You'll understand this much better if you try the code out for yourself and play around with it to explore other possibilities. Debugging is annoying, but it teaches you a lot, trust me. You might be asking yourself, wait, why would I want to use linked lists? They're very handy when you don't know how many elements you're going to have in your array. Instead of creating huge arrays and wasting memory, you can just allocate space dynamically, i.e. during runtime, and attach as many elements to your list as you like. This brings me to the final part of this video, which is about the advantages and disadvantages of linked lists versus arrays. First, it's faster to access array elements because they're allocated in sequence. Elements can be accessed randomly. Also, with arrays, you just need to remember the first element's address and its length. The rest of the elements can be accessed through mathematical operations. However, arrays are inflexible for two reasons. First, their size is fixed, so you can't add or remove elements easily. Secondly, you need to know how many elements are going to be in your array in advance. This doesn't happen with linked lists because you can add new nodes dynamically. In that respect, linked lists are very flexible. However, it takes much longer to access individual elements in linked lists because you have to go through all the nodes before the one you're looking for. This means that accessing elements has a complexity of O of n, whereas in arrays, this complexity is O of 1, i.e. it's constant. There's no sequential allocation, like in arrays, so you have to keep track of each node's address. That's an additional memory overhead. Linked lists are usually used when there are not that many elements to store so that access time is negligible. One example of this is hash tables with chaining. Since data values in hash tables are sparsely distributed, linked lists inside each hash cell don't get too long on average. To wrap up, I'd like to note that this is just the very basics of linked lists. There are also doubly linked lists, binary trees, circular lists, etc. I'd encourage you to discover them for yourself as well because they're even more interesting than singly linked lists. Welcome to the exciting world of data structures.